David Montgomery.
Thank you. Great. Thank you for the invitation to come and talk to you all today, and for the sponsorship and for the United Airlines for getting me here yesterday. I'm a geologist, so first off I'll say that I'm probably not the right person to talk to anybody about how to grow crops. I deal with rocks, and that got me into soils, kind of indirectly. Because when I was an undergraduate, my professors basically told me that soil was not important, the important stuff was below the soil. You have to clean the soil off and get the rocks, the real stuff you're supposed to study as hard rock geologists. But over time, I actually came to appreciate soil as one of the most fundamental resources that humanity has. So the reason that a geologist like myself would write a book about soils that actually evolved as I was writing it into a book about the history of farming is that essentially, as I started to look into the role of soils on civilizations, both ancient and modern, I started to really come to see that soil probably needs to be seen as perhaps one of our most strategic resources. We tend to think of things as strategic resources like oil or water or perhaps the atmosphere. Soil is the one that tends to get relatively neglected in long-term strategic thinking. And yet if you look around the world today, and as I'll show you if you look at the world in the past, global soil degradation or regional degradation in the past really is one of the big underappreciated environmental crises that we face as a species over the next 1 to 200 years. The kind of time frame that a geologist like myself thinks is shockingly fast, but that never quite enters into the sort of strategic planning on a societal level. Now, what is the state of global soils today? Well, this map from the United Nations basically shows sort of a very broad brush image of global soil degradation. You'll notice there's a lot of yellow and red areas where regionally soils are somewhat degraded to very degraded. And if you superimpose on this map the sort of global population density, you'll recognize that where there have been people for a fair amount of time and agricultural practices for a fair amount of time, the soils are somewhat degraded. Well, this is a broad brush. You could look within any of those red zones on the map and find incredibly well-run farms that are building soil rather than degrading it. So again, this is a very broad brush. But how fast have we been losing soils for the last half century or so, or perhaps the last century actually? Well, over the last 40 years, as of 1992, when this estimate was put together, in other words, since the Second World War, soil erosion and land and degradation have caused farmers globally to abandon some 430 million hectares of land. That's an area equivalent to about 1/3 of all the world's present cropland, an area the size of China and India combined. And if you think about the fundamental problem of how are we going to feed the world in the second half of this century, it would certainly be very useful to have that 1/3 of the cropland we had a century ago back in the state it was of full productivity back circa the Second World War. Well, how fast is the rate of soil loss today? Well, if you look at the global pace of soil loss off of agricultural fields, I'll show you data a little later, we're losing about 23 billion tons of topsoil a year. That's about 0.7% of the world's topsoil inventory each year. And it's not magically disappearing, it's being removed from one place, put to another. But it's, once soil is out of where it's supposed to be, it then becomes dirt, which I forgot to not apologize for the title of my book at the start of the talk. I know very well you are never, ever, ever supposed to call soil dirt. But once it's eroded off the farm field, it actually becomes dirt, thereby the pun of the title. So this got me off the hook with the guy who taught me soil science, at least he bought that explanation. But the rate of loss of less than about 1% a year is pretty slow. Who sort of worries about losing less than 1% a year? I mean, that's about the rate that a bank will give you interest today. It's functionally zero. Unless you think about it over century kind of timescales, the kind of timescales that a geologist considers relevant. If you take the pace of modern soil loss and project it out into the future, at that rate it would only take 150 years to completely denude the world's agricultural lands of topsoil. Now, I'm not standing here telling you that we are going to, in fact, run out of dirt. It's kind of like saying we're going to run out of oil or run out of air. It's not going to happen. But something that actually is lost faster than it's being produced for long enough does become scarcer. And that, I think, you can project with these numbers into the future as a certainty, unless, of course, something changes. Well, I want to spend the first half of this talk essentially talking about the past. Well, I'm a geologist. It's a historical science. I've been fascinated by it and study the past. And I've been very interested, since I was an undergraduate, at the things that actually control the longevity of human civilizations. What actually sets the time span, the lifespan, if you will, of societies. Now, there's no real mystery that some of the key controls are things like climate changes, natural disasters, and politics, war, and social evolutions, or humanity's propensity to not be very good about sharing toys and playing with our global neighbors. For example, in terms of climate changes, the Viking colony in Greenland is a very well-known example of a civilization that tried to get a toehold in an environment that then shifted to a colder period during the cold snap of the Little Ice Age, and they got basically frozen out of Greenland. Certain Egyptian dynasties were wiped out by extended droughts. So there's really no mystery that a changing climate can actually take down a vulnerable society. Similarly, natural disasters can take down societies. There's no real argument there. The poster child for that is probably the Greek island of Santorini, that back in the Bronze Age, about 1500 years BC, basically disappeared overnight when their island homeland erupted out from underneath of them. They built their home city, in other words, and it's a place analogous to Mount St. Helens up there in my home state of Washington, in the upper right-hand corner. Not a very good place to build a city when the volcano does erupt. So why would you build a civilization on an active volcano in the middle of the Mediterranean? Well, this is the Bronze Age. They had geothermally plumbed hot running water 3,000–4,000 years ago. They were one of the most technologically sophisticated societies in the world at that time. They just didn't know a lot of geology. They were very poorly sited. And the point I want to make with that is that in terms of the resilience of societies to natural disasters, scale matters. If you're a small island civilization, basically when your homeland erupts out from underneath, it's game over. Their civilization ended. A large nation like ours, or an integrated global society, the way we've been moving for the last century, can in principle at least take aid from an undisturbed area to an area that has been subject to a disaster, and therefore there should be more resilience in larger civilizations. And of course, politics, war, and social evolution, there's no argument that that influences the course and fate of civilizations. That, after all, is what you get when you read history books. But what about the soil? The question I wanted to ask in researching this book is, could the way that people have treated land historically influence the longevity of civilizations? Because after all, the fundamental conditions for sustaining a civilization, an agricultural one in particular, which darn near every civilization that's ever been, has been, and probably ever will be, is sustaining the soil and the fertility of the soil, the physical body of the soil, as well as its ability to produce food. Well, that's not a terribly new idea. In fact, a lot of what I'm going to be telling you, I'm not trying to take credit for as radically insightful new ideas. I'd like to recycle ideas. Again, geologists are really good at that. But soil erosion, if you look back at environmental history textbooks, you can find the ideas that soil erosion resulting from deforestation has been proposed to explain the demise of civilizations around the world. All those civilizations over on the right-hand side, so running off the right-hand side of the screen over there, I could extend that sort of down at least equally far at the bottom. I go over examples of all of them in the book. So that's not a terribly new idea, but I started to come to realize the standard idea of deforestation caused soil erosion, wiped out societies was probably too simplistic. For a simple reason, really. I started doing my geologic studies of erosion in the Oregon Coast Range. It's steep forested terrain where it's been timber intensively managed for forestry for well over 100 years now. Places where they're in the third, fourth cycle of timber rotations. And you do indeed get a pulse of soil erosion that results after you clear cut a 45-degree slope. Well, you know, the trees grow back pretty darn fast. And if you actually run the numbers, you can't possibly explain the wholesale loss of the soil off the landscape, as we've seen, and I'll show you in a minute, in ancient environments, from simply cutting the trees down. That they grow back too fast. So it started me asking the question of, well, could the plow have actually been the culprit that followed the axe and caused the kind of wholesale regional soil erosion that actually has affected ancient societies, or I wouldn't have been able to essentially pull my argument together and publish the book, and so the title kind of gives away the answer. So I wanted to wrestle with the question of, could agricultural soil erosion and degradation actually limit the lifespan of civilizations? And you'll probably find the first half of this talk rather depressing, but I'd like to try and assure you that there is a positive ending to it. That there is a relatively optimistic message that one can pull out of it. even if the historical record does, make you want to kind of jump off a bridge occasionally. Well, there's been a number of archaeological studies recently that have showed that soil erosion, confirmed really the role of soil erosion in the demise of ancient civilizations, ranging from sort of early societies in Neolithic Europe or sort of the Bronze Age Europe, classical Greece, Rome, the southern United States, Central America, get at Easter Island, northern China. You can sort of, the list really does go on and on. I'm going to give you just a couple examples today. I'll spare you sort of all the examples I could go through, because what you tend to see, what you do see when you put them all together is a recurrent pattern. And I'd like to emphasize that pattern and then talk about what it actually may mean for the future of society. But first, let me invite you to think about soils the way a geomorphologist like myself does. Because I'm that kind of geologist that studies the evolution of topography. Geomorphology is earth form science. So 100 years ago, I might have been called a physiographer or a topographer, but I study landscapes, how they evolve over time. And that can range from the short time when a single rainstorm can cause rills across a farm field, all the way up to the evolution of things like the Himalaya and the Andes. But the way someone like me thinks about soil is as a system, something that's produced from the weathering of rocks over there in the lower right-hand corner of the screen, that gets mixed and integrated with biological material, both living and dead, to create soils. Because soils are essentially, I like to view them as the interface, the boundary, the border between biology and geology. It's where the two meet and merge. But if you also then think of soils as a system that erodes, if you're on almost any kind of a slope, whether it's a ½ degree slope or a 45-degree slope, the soil is moving downslope over geologic time. It's mobile. And so if you think, therefore, about soil as a system that's produced from weathering and that's lost from erosion, you can start thinking about the standing crop of soil in a landscape as essentially the storage that represents the integrated time difference between soil production and soil erosion. Think about it the way you do your bank account. You have income, that's the weathering of rocks to produce soil. You have expenses, that's your erosion. And you've got your savings, that's the soil that's on a landscape. And I like to use this example. This audience is probably well tuned to knowing this. When you talk to sort of a general audience in the public, people don't tend to think of soils as things that change over time. Why will they change so slowly? In our lifespans, we tend to look out at the landscape, and it's much the way that we saw it, when we were younger. It's only in retrospect after a lifetime that you can essentially see these changes add up firsthand. And yet we know from our experience with our bank accounts that any kind of a system where you use something faster than you make it, you spend money faster than your income, you're basically burning up your savings. Soil is really no different. And it's no different whether on an individual farm or at a national or indeed international level. Now, where is it that essentially we get back to the hypothesis of how long-term farming practices might have influenced the fate of civilizations through the effect on soil? Well, essentially, you can go back to the invention of the plow. And you can actually trace the acceleration of erosion in ways that influence ancient societies pretty much right back to the Mesopotamian invention of the plow. Why would the plow essentially have such a long-term effect on soil on the surface of the earth? Well, think about what happens when you turn the earth and leave it bare and vulnerable to winter rain for some portion of time. It can erode faster than the soil can rebuild. And there are special places where the soil can build fairly fast, but as I'll show you a little later, if you actually look at the modern data on soil erosion rates, we're kind of running a losing battle by continuing to rely on plow-based agriculture at an international level. And the sort of analogy is if you go out and look at a native grassland or if you look at a native forest, there's very few places where you have land that's bare ground during the season where you can expect the biggest storms. Yet that is actually what has happened in many regions that have relied for centuries on plow-based agriculture, what I will call conventional agriculture. Well, let me show you a few examples from the historical record that make this case. Then I'll show you some more modern data, and then I'll try and make a more forward-looking argument. Well, you can find cycles of soil erosion and formation that began in ancient Greece in the Bronze Age with an erosion event literally right after the arrival of plow-based agriculture. Why do I use this one? Well, because essentially Tjeerd Van Andel and Chris Rummels put together the story for this back in the 1980s when I was in college, and they've already done the work, so I can pick it up and use it to make my point. You can make a similar point, though, in Mesopotamia, in Syria, in Jordan, in Israel, in Rome, in North Africa, in parts of Southern Europe, and the list does kind of go on. The symbol model you see, though, is if you take a cross-section of a hillside, this is back when, right after deglaciation, it's Van Andel and Reynolds' model of what the Greek landscape looked like. You had open oak woodland with those vertical bars representing a 1 to 3 foot thick soil on the hillsides. And when agriculture arrived in this environment, it started down in the valley bottoms, while it was flat, relatively easily worked land that was watered by the streams that were flowing through. It was the logical place to essentially start. As the population density rose, cultivation spread up onto the hillsides, and literally grain fields were grown right up to virtually the crests of the divides in the southern Greek landscape. And that started a cycle of erosion running faster than the soils were being rebuilt naturally. And over time, that intensive cultivation stripped the soils off the hillsides, piled them up down in the valley bottoms, extended the deltas so that the ancient cities are now well inland of where the Mediterranean still stands. And how do we know this? Well, we can find bare areas of rocky soil with maquis vegetation where you could not possibly grow grain today, where you find Bronze Age agricultural implements still scattered across the landscape, where it was farmed, but there is no soil today. Fairly compelling evidence. And the problem, of course, is not so much that the soil has completely disappeared, but that they took a layer that was 1 to 3 feet thick, spread over most of the landscape that could be worked to support a population, and it ended up piled up in the valley bottoms. So you took a thin layer and made it a thick layer, and essentially the ability to produce food off the land is not a function of the volume of sediment on the landscape, it's a function of the surface area with productive soils. Well, what did this do to the population density in southern Greece? Again, Van Andels and Reynolds put the story together a few decades ago, but they had the audacity to essentially plot population density for the southern Argolid, a particular valley, against time. And it's 6000 BC over there on the left, so I guess I'm not tied into anything, so I can walk over here. Basically, it took a couple thousand-year run-up of population during the Bronze Age. It crashed then in the period just after the Bronze Age, and there was a dark age before the run-up in population to the classical Greek period, and then a second crash, and then a third rise. Now, clearly, I'm going to try and relate this to soil erosion and then reformation between the intervals of population, because that's the point that I'm trying to make. But it kind of works in the Greek landscape. There's not many other places in the world that you can point to where you've had 3 agricultural civilizations on the same area of land over time. Or at least, and certainly not where the geology and archaeology have been done to reconstruct a graph like this. This was the graph that really got me thinking about, well, could long-term soil loss off of agricultural fields essentially be driving the pace of this several thousand-year run-up, and then a crash for a couple thousand years, and then a couple thousand years more, and repeating. And again, I'll show you data that essentially supports that argument in a little bit. But this is the figure that got me really thinking about that. And of course, the figure that we'd really like to know is, if you view this at a global scale, what comes off the right-hand side of the graph? Are we really essentially, since we've already established that we're gradually lowering the supply of fertile topsoil on the planet, and we all know that the human population is still rising at a somewhat alarming rate, what's going to happen off the right-hand side? Are we setting ourselves up for a global calamity? The good news is that we don't have to. The bad news is that we might be on our way towards it. Well, I'm not the first person to suggest a connection between the way that people treat land and the duration over which land would be able to support large human populations. Plato actually suggested this, the Greek philosopher, back in the 4th century BC. He was writing at the time of the peak in classical Greek history, and he wrote about the erosion event he read in the topography of southern Greece from the Bronze Age. So he was looking from the second peak back at what happened in the first peak. And he wrote, in describing the Greek landscape, that the rich, soft soil has all run away, leaving the land nothing but skin and bone. But in those days, the Bronze Age in this time, the damage had not taken place. The hills had high crests, and the rocky plain of Phelus was covered with rich soil, and the mountains are covered by thick woods, of which there are some traces today. He was looking at things like olive trees on close to meters, several foot high pedestals on the margins of plowed fields, and he kind of connected the dots and basically made the case that their long-term practices had stripped the soil off the landscape, and he then went further and complained that this was why Greece was not able to raise the big armies that it had in previous times and keep the Persians out. Well, let me skip over Rome and North Africa and Southern Europe and use as the second example of colonial North America. Why? Well, it's our country, and we ought to be thinking about the history of it. And it turns out that soil erosion played a far greater role in the history of the United States than I was ever taught in the American history classes I had in high school and college. And I got very intrigued about that when writing this book up. What was the sort of the instigating connection? Well, tobacco was essentially the vector originally in the early colonial states. Why? Well, tobacco was essentially a very erosive crop the way it was grown in colonial times. You could get about 3 to 5 years of a productive crop out of the thick, rich black earth that covered the southeastern part of the U.S. At colonization, or at European colonization. And you would then move on and essentially clear new land once that you had exhausted the initial clearings. And about 100 years after the establishment of the Jamestown colony, Hartwell, Blair, and Chilton described how virtually everybody in the colonies was growing tobacco. And they wrote that so it is at present, that tobacco swallows up all over things. Everything else is neglected. By the time the stumps are rotten, the ground is worn out, and having fresh land enough, they take but little care to recruit the old fields with dung. There was a real difference in the late 17th and early 18th century in thinking about soil between the American colonies and in Europe. In Europe, land was very expensive. People were cheap. They were exporting people like my ancestors as fast as they could throw us out of Europe and sending us off to North America and Australia and New Zealand. But land was really expensive. And whereas in North America, land was cheap. You just cleared more land if you needed it. Labor was expensive. And so you had completely different economics of colonial and European farming. And in Europe, strategies of crop rotation, animal husbandry, mixed livestock and cropping, all started to be developed at around that time as large landowners tried to increase the value of their land that had been already degraded by a millennium of farming. In North America, it was completely different. There was no such incentive, as Hartwell, Blair, and Chilton pointed out. Well, this led to incredible erosion in the southeast, as I'll show you on the next slide, the magnitude of it. But the kind of erosion that happened in colonial North America was widely recognized at the highest levels of American society. George Washington, for example, in a letter to Alexander Hamilton in 1796, in writing about the state of plantations in his neighborhood, wrote that a few years more of increased sterility. He was complaining about declining crop yields in the 1700s. A few years more of increased sterility will drive the inhabitants of the Atlantic states westward for support, whereas if they were taught how to improve the old instead of going in pursuit of new and productive soils, they would make these acres, which now scarcely yield them anything, turn out beneficial to themselves. Washington was basically arguing that the future of the United States would inevitably lie in westward expansion across the Appalachians, not because of a manifest destiny to civilize an untamed continent. That argument was applied as reverse engineering around 1900, 1890 or so, if I recall. He was predicting a century earlier that this would happen simply because the soils of the eastern seaboard were being exhausted fast enough that a nation of farmers would be moving over the mountains to take advantage of the soils of Kentucky, Tennessee, Indiana, Ohio, the South. His was a fairly prescient prediction. How bad was the magnitude of historical soil erosion in the Southeast? Well, this is a map that shows you the extent of historical soil erosion in the Piedmont regions, the upland hill country. The areas that were underlain had thin 1 to 3 foot thick soils analogous to southern Greece. So you're not talking about the coastal plains from Georgia to North Carolina or the high Appalachians. You're really talking about the hill country that was actually a very major producing land in colonial times. And as you can see, 4 to 10 inches of erosion occurred across much of the region. More than 10 inches in some places. Well, is that a big deal or a little deal? There was only about 12 inches of thick, rich, black topsoil across this region to begin with. And this is fairly well-constrained data. I've been to some of these areas, and there's no A horizon left when the soils are being farmed. They're basically farming the B horizons. The topsoil's gone. Now, if we can do this in just a couple hundred years since colonial times, over an area that was originally the breadbasket of our original colonies, Imagine what the Greeks and the Romans could do with 1,000 or 2,000 year run at it. What the Greeks did a couple times. What the Chinese could do, what the Eastern Islanders could do. It starts to put the idea that slow, long-term agricultural soil erosion could actually lead to the wholesale stripping of soils off the landscape in ways that forestry never could really manage to pull off. Now, extensive soil erosion in the Piedmont did not occur because of ignorance of soil conservation practices. If you look at some of the writings of a gentleman named Hall, who worked for the USDA in the 1930s, and was charged with trying to evaluate what kinds of soil conservation practices should be used in the aftermath of the Dust Bowl to try and cut down on soil erosion, because the Dust Bowl, of course, was a time when the American government got fairly serious about trying to limit soil loss off of American fields. Hall basically looked back and determined that most of the erosion control practices in use at the present time, in the 1930s, were either developed by the Virginia farmers back in colonial times or became known to them during the first half of the 19th century. In other words, things like contour plowing and terracing, cover crops, the kinds of things you could do to cut down on the kind of erosion that would lead to gullies like the one I'm showing here in North Carolina that started in agricultural fields. The methods for minimizing erosion were actually known during the early 19th century, virtually in George Washington's time. So this could motivate the question of what would essentially motivate a nation of farmers, because we've always been and particularly in colonial times, been an agricultural nation powerhouse. Why would a nation of farmers treat their land in ways that over time would essentially limit the ability to further that activity? Well, a sociologist named Anthony Craven, I think, hit the nail on the head, missing sort of one thing, which I'll get back to, which is the slow pace of soil loss. Soil erosion is kind of like death by 1,000 cuts. It's insidious. It happens slowly enough not to be the crisis du jour. But Craven basically identified, I think, some of the underlying social and economic causes when he wrote that men may, because of ignorance or habit, ruin their soils. But more often, economic or social conditions entirely outside their control lead or force them to a treatment of their lands that can only end in ruin. You can trace those kinds of pressures all the way back to Roman agriculture, when Roman agriculturalists were essentially compelled to work their land continuously and hard to pay off the debt they went into to acquire the farms and to acquire much larger estates. And that pattern is essentially played out in society after society. Or if you think in terms of the other classic example I explore in the book is the role of tenant farming in the American South in the run-up to the Civil War. If you don't own the land and you're moving from farm to farm every year, as was the pattern in those days, what's your long-term interest in maintaining the fertility of the land? Well, it's fairly marginal. Your interest is in maximizing this year's production. And therein lie both cultural and social and economic traps that whole sectors of a nation can fall into that favor long-term land degradation. Now, I like to show this slide of my home state, Washington State, and eastern Washington in the Palouse, because it illustrates why a geologist like myself would consider what I call conventional cloud-based agriculture to be such a long-term problem. This is a field, it's a winter wheat field in the Palouse. There's nothing on the field. Single rainfall can generate the kind of small channels and rills that you see here. This is in the 1970s. I can show you some pictures. There's still places you can find examples like this. And you can plow right across them. I mean, these are truly rills. One pass the plow would wipe them out. They're not gullies big enough to drop a tractor into yet. And they form essentially every year. And to a geologist like myself, this is just like soil bleeding off of the landscape. And how fast can that actually add up? Well, if it happens every year, it can add up to a shocking amount of soil erosion over a relatively short time, a single lifespan. This again is a photograph from the Palouse. The fence up there in the upper right-hand corner is a fence that the farmer who cleared this originally started farming this field in 1911. It had been nothing but used to grow, I think it was winter wheat, between 1911 and 1961 when the photo was taken. He basically built that fence around his water cistern so he wouldn't plow over it. And you'll notice that there's a bit of a cliff on the edge of that at the upper end of his field by 1961. And what you can't see very well, but there's a little black stripe right above where I'm pointing that is probably about that big on the screen, but it's a 1 foot increment on a stadia rod that shows up beautifully on the old negative, but never projects very well. It's kind of washed out. But that's about a 5 foot cliff at the edge of this field. That's 5 feet of erosion in 50 years. That's about a foot every decade, or in other words, an inch a year. And I'll show you a compilation of data in a minute of how fast soils form globally. There's nowhere on Earth that soils form at a pace of an inch a year. Now, I'm showing you this because it's an extreme example. That's why I like it. It makes people it's kind of like the photo I have of somebody moldboard plowing a 45-degree slope. It's kind of like, what are they thinking? It's an extreme example. So the question you ought to be sitting there asking yourself is, okay, so you found like one really extreme example. How typical is this? Well, that's exactly the question I wanted to ask myself when I started to put together this argument that, and test the argument as to whether long-term erosion off of conventionally plowed fields could undermine societies. How would you test that? There weren't geomorphologists out measuring soil flux or erosion off of Roman agricultural fields. We have no data from classical times. But there's an awful lot of data today around the world where people have measured soil erosion in different contexts and settings. So I did something that has become incredibly unpopular among undergraduates, and that is I went to the library and I did research. I basically vacuumed up all the data I could find over a period of about 3 weeks when my grad students are out in the field, school's out of session, and I really wanted to test whether the ideas I've been putting together by looking at the historical record, ancient societies, whether modern data bore out the argument. In other words, was the pace of soil erosion over a large enough scale fast enough to maybe explain that 1 to a couple thousand year time frame we saw in classical Greece and that we see in many other societies. So I went and gathered data on long-term erosion rates, geological erosion rates. Why long-term rates? Well, if the balance between soil production and erosion in natural systems are about the same, long-term erosion rates are about long-term soil production rates. And they need to be that. If you're dealing with geologic time, imagine if soil erosion was faster than soil production, if you have geologic time to work with, the world would be a bare bedrock landscape. So the fact that we have soils on most of the world's hillsides effectively demonstrates that the long-term erosion rates, they're more or less going to be the order of magnitude of long-term soil production rates. So this is the data that I found. I found 1,400 studies, and yes, there are boxes full of papers in my lab that document all this. And I did not include any universal soil loss-based modeling studies. I wanted to include real data, no model results. And they'll spare you the diatribe about why that is. But I wanted real data. And so all the white data points and stuff that labeled craton, soil mounted, and alpine glaciated, those are long-term natural geologic erosion rates. The black data points up in the corner we'll get to in a minute are conventional plow-based agriculture globally. Old world, third world to data from this state and the state of Washington. So a whole spectrum of the world. Notice that the rates of erosion on the world range tremendously, 7-8 orders of magnitude. The slowest rates you can find naturally are over here, where there's about 1/10,000th of a millimeter a year. I challenge you to figure out a way to measure something that happens that slowly. It's really challenging. Over on the far end, that one data point sitting up there in the Alpine Glacier at the far right, separated from the others, is the gorge of the Sanko River in eastern Tibet. It's the fastest eroding place on the planet. It's the place where the National Geographic kayakers got in and disappeared. Nobody ever saw them again. It's incredibly erosive. I've stood by that river. You just how they fought to get into it is just, they're a lot braver than I am, but I'm still alive. So you have these sort of three areas. What are cratons? Those are flat, dead parts of continents, flat tectonically dead parts of continents, where the world's plates are no longer pushing together. So it's like where we're sitting, we're in the middle of a craton. Heart of Africa, heart of North America, much of Russia, sort of the areas where you don't have steep mountains. And they erode very slowly, less than about a 1% of a millimeter per year is kind of the upper limit to what you get in cratons. Soil mantle terrain, that's sort of things that have a little more relief to them. Slopes that can get up to 10 to 30 degree kind of slopes, but that have soil over them. They erode at rates up to about 1 millimeter a year or so. The stuff labeled alpine and glaciated terrain, those are like real mountains. That's the Cascades, it's the Himalaya, it's the Andes. It's places where you wouldn't think that you would actually farm unless you had no other land. The Nepalis and the Tibetans will farm that kind of terrain, but only because they don't have anything else to farm. Now I'll essentially look at the data that's labeled agricultural, the long-term, the erosion rate data from plow-based agriculture. And just play the experiment in your mind of which geologic environment are those most like, and where are they most like? And what you basically come to is a conclusion that conventionally plowed farms essentially erode like alpine topography. We've managed to turn places like Nebraska, Tennessee, Illinois, viewed at a broad scale into areas that erode like the high Himalaya at that same kind of a pace. And that's actually quite an achievement if you think about it. It's not necessarily our proudest achievement as a species, but it's a pretty major one nonetheless. The other thing I want to point out is that vertical red line is essentially what the USDA has defined as tolerable soil loss values that range from about 0.4 millimeters a year to about 1 millimeter a year. And if you compare those, and you notice they run sort of right through the middle of the agricultural data, and we'll talk more about that, but compare it to the soil mantle and craton data, the long-term geologic data from those parts of the world that we might actually think we could sustainably farm, because we're not going to sustainably farm the high Himalaya, so we'll just leave that stuff off. What's defined as tolerable soil loss is at the far right end of any kind of reasonable long-term rate of soil production. In other words, conventional, what we've defined as sustainable agriculture isn't. Now that's the bad news slide. This is actually the good news slide. Why is it a good news slide? Well, I collected some more data that I haven't told you about yet. And so what I've done here is I've added a second axis. So the y-axis is now erosion rate, and the x-axis is a percentile plot. So I'm just showing you literally all the data that I compiled. Each one of those dots is a different study. And it shows you the probability distributions for geological erosion rates. That lower black line combines all the craton, soil mantle slope, and high altitude terrain data. It's the line that shows you how fast does the world erode when you're just looking at the whole world. The upper black line, that's the conventional agricultural data. Again, plow-based agriculture, the way that I'm using the terminology. And there's 3 other data sets that are shown on there. One, the white data points. One for rates of global soil production. One for rates of erosion under native vegetation, sort of how fast landscapes erode under the vegetation that they had pre-agriculture. Notice that they both plot pretty much right on top of the long-term geological erosion rate data, validating the idea that, yeah, soils form about at the pace they erode under the kinds of vegetation that have evolved naturally in most landscapes around the world. It all kind of balances. The last data set, labeled conservation, that's essentially conservation agriculture. It's fields that have been managed with no-till agriculture, with terracing, with essentially a lot of attention to soil conservation. You'll notice it plots virtually right on top of those other data sets, including the long-term geological erosion rate data. In other words, the problem that we have had historically with agriculture is not simply the fact that we farm. That would be a horrible conclusion to actually come to, particularly to stand before you all and talk about. We can demonstrate with the global data compilation that you could arguably maintain very intensive agricultural productivity and thereby civilization in a way that is not going to deplete the soil at a pace over a time frame that a geologist like myself would consider relevant to the problem of sustainability. In other words, the problem is not that we farm, it's how we farm. And that there are ways to actually farm very aggressively that would preserve the soil itself. The problem, of course, is that viewed globally, those practices are still considered alternative agriculture rather than mainstream agriculture. And it's my contention that over the course of the next couple hundred years, and again, because as a geologist I can get away with thinking on those kind of time frames, we're going to have to essentially convert what we call now alternative agriculture into what we will then call conventional agriculture, or we're going to face the same situation that the classical Greeks did. The good news is it's going to happen probably after I'm dead, so I'm not I'm not losing a whole lot of sleep over it this week, but I am trying to talk a lot about it because I do have an interest in the future long run. Now, let me show you just one more slide in terms of the actual data before I shift focus a little bit. And that is, I know those probability distribution functions can be a little odd to think about and look at. If you just think in terms of averages, I can tie this back to this thesis that I started the talk with. So whether you think in terms of a median, whether half the data values are larger than or half smaller, or a mean, where if you just average them all up, and we take the close to 500 studies that I've looked at for conventional cloud-based agriculture, the median, the mean, or the average erosion rates are somewhere north of 1 millimeter a year. You look at all those other blue numbers up there, the erosion rates under no-till agriculture, under native vegetation, rates of soil, long-term rates of soil production, long-term geological erosion rates, or another way to measure long-term soil production. Those blue numbers are all about 1/10 of a millimeter a year or less. I'm not going to argue to you that I can tell the difference between any of those blue numbers. They're small relative to the red numbers. That's the key point. And the difference is on the order of at least 1 millimeter a year. And that's conservative. It's the bottom, it's below the bottom end of the data that I'm showing you. Now, if we take that conservative estimate of the current pace of long-term soil erosion off of agricultural fields globally, and we apply it back to that problem of what sets the longevity of civilizations, we can do a little simple back-of-the-envelope math and essentially support the point that I started with. So if we think of net soil erosion under conventional agriculture on the order of 1 millimeter a year or so, it implies that it would only take about 500 to 1,000 years to erode the typical 0.5 meter to 1 meter, like a 1.5 to 3 foot thick soil, off of a hillside that is fairly typical globally. Consult the UN Global Soil Database, and that's fairly realistic. That 1,000-year kind of time frame, and to a geologist, 1,000 years plus or minus 50%, that's pretty precise. That's approximately the lifespan of most major civilizations, with one really big set of exceptions. And that is, of course, the civilizations that grew on major river floodplains. The Nile, the Indus, the rivers in China. Why would those last for thousands of years in the face of long-term soil erosion? Well, because on a river floodplain, it's erosion of the uplands that's going to refertilize that floodplain every year. You can thank Ethiopia, which is hardly the sort of a vision of economic productivity these days, for the long-term sustainability of Egyptian agriculture in the Nile, which the Egyptians had a great run on until they built the Aswan Dam, and now they're the biggest users of fertilizers in the Middle East because they've cut off their own natural supply of native soil fertility. So the long-term exceptions you can immediately point to in terms of very long-lived societies actually, I think, help make my point. Walter Lauterbach, a soil conservation service scientist back in the 1950s, made pretty much exactly the same point before I was born. He wrote that here in a nutshell, so to speak, we have the underlying hazard of civilization. For by clearing and cultivating sloping lands, for most of our lands are more or less sloping, we expose soils to accelerated erosion by water or by wind. And in doing this, we enter upon a regime of self-destructive agriculture. He pretty much had the problem I've just laid out pretty well framed 60 years ago. So did Franklin Delano Roosevelt in the aftermath of the Dust Bowl. He put it even more pithily when he basically said, a nation that destroys its soils destroys itself. That's as true today, and perhaps even more important today than it was in the aftermath of the Dust Bowl, because we're now essentially faced with thinking about this problem at a global scale. This, of course, motivates the question of, well, can we reverse this historical pattern? Is soil restoration possible at a global scale? I will argue to you that it is, and it not only is, it's imperative that we do so. And so how might we go about it? Well, as I was writing Dirt's book, and thinking about putting together the story of ancient civilizations and how they sort of cut their own legs out from under themselves by farming too long on the same ground with the same practices. My wife was restoring the soil in our yard in North Seattle. I live in a place that was glaciated, completely stripped off once by glaciers, the soil rebuilt to actually support the old growth forest of the Northwest, which had the highest standing biomass of any forest in the world. It beat the tropical forest by a lot. It then got stripped completely back to the old glacial till when our neighborhood was developed around 1918. So when I got the house 90 years later, we had a 6-inch lawn on glacial till. It was virtually nothing. And my wife's a gardener. She wanted a garden. We forgot to actually dig a hole in the yard and look at what our soil was like when we bought the house. Yeah, go figure. Geologists shouldn't make that mistake, right? But the point I want to make is that it took her about 8 years of intensive composting and mulching and trying to bring organic matter back into our soil to start building a several-inch thick A-horizon. She was building soil at a pace of several inches a decade. This is orders of magnitude faster than the pace that soils naturally are built. And that sparked a revelation in my mind that nature wouldn't be able to rebuild soils fast enough to actually matter in terms of the longevity of human civilizations. We kind of burn through the supply and have to wait a few thousand years for nature to catch back up to us. But people, through the application of energy, labor, and intelligence, actually could rebuild soils far faster and at a pace that actually could matter to essentially completely undermine this cycle of land degradation that we've seen in society after society. And this is sort of what got me so interested in no-till agriculture and other agricultural techniques, the soil building techniques, soil health as an emerging emphasis in agriculture. Because I think that if we really put our minds and our creativity and our energy to it, we could reverse this historical pattern. It's been done in the past. There's a few societies that you can point to. I point to 3 in the book. I'll mention a couple here that have actually built very fertile soils. The Dutch, for example, built very fertile carbon-rich soils in the areas that they walled off from the sea because they got pinned in by their neighbors. They weren't powerful enough to defend, to basically claim new land. Their population was growing. What they did is they walled off parts of the sea and started to reclaim that land. How did they do it? By returning their urban organic waste and their organic waste off of fields to the newly reclaimed land. And they built some of the richest, blackest soils in Europe, the so-called plagan soils, on top of beach sand. And they did it within the span of a few decades. In other words, very rapid, very focused soil building activities. The Amazonian Indians, at the other end of the historical spectrum, built the best soils in the Amazon, the so-called black earth terra preta soils, in areas where the native soils are incredibly infertile. Tropical soils are not very fertile for the simple reasons that it's really hot and it rains a lot. The nutrients are stripped. Basically, the soils are iron and aluminum rich. All the nutrients are in the standing canopy. When you clear the forest, you've taken the nutrients away. You can't farm it for more than 5 years productively before basically you have to move on to new land. It's a lot like colonial tobacco cultivation. But the native Amazonians built the best soils in the Amazon around their highest population densities. More people meant better soil. How did they do it? They did it by returning their cooking fires to the land, by essentially returning their village wastes to their fields. They cycled organic matter back into their soils and built up the best soils that are good enough that today they're mined as potting soil and shipped to the big cities in Brazil. In other words, people can build soils remarkably fast. And there's examples that we point to where it was human activity that really built the fertile soils that could maintain human activity, thereby offering the potential to break the historical cycle. So why would we also want to bother restoring soils globally? Well, the point I'll make is that it could be to address some of the biggest global challenges we have in the 21st century. Restoring soils could help us deal with the problem of climate change. It won't solve it, but it'll help, no matter what you think is causing it. It can help us feed a post-oil world. It could improve public health and city livability and help contribute to preserving biodiversity and environmental degradation. 4 of the biggest problems that I would maintain that humanity faces this century are all things for which restoring soils, and by that I mean restoring healthy, fertile soils, could be partial solutions to all these problems. And I don't know of a single other, single idea or single policy level change one could make that could help to contribute to all 4 of these problems. And I think that it's particularly pertinent to ask the question of what's going to happen after we pass the era of peak oil, which we're either at the crest of now, slightly after, slightly before, however you want to think about it. Using oil industry data, you look out to the right-hand side of where we're at over there at 2013, and basically oil is going to become increasingly scarce for the next century. There's no possible reason to expect it not to do that. I don't expect it to become any cheaper in the next century. I expect quite the opposite. And it basically motivates the question of how are we going to maintain our level of agricultural productivity at a global level with agricultural systems that are as dependent on oil and energy as they are today. In other words, how are we going to feed a post-oil world without cheap, I should have the word cheap in there, cheap fertilizer-intensive agriculture. And you may all not think fertilizers are cheap, but by the standards of maybe 50 years from now, they may very well be. I don't think the prices are going to be going down in the next century. And I'd like to offer the idea that in order to basically feed the world 50 to 100 years from now, we're going to have to start thinking a little differently about agriculture, if only for the reason that we need to start conserving soils better so we don't have our declining soil availability curve impact the rising population curve and inadvertently prove Malthus right. But there's enough studies in the last 20 years that I could find to show that crop yields from no-till and organic agriculture can compete with the yields of conventional agriculture and over time greatly exceed them on degraded land, to basically argue that one of the biggest enterprises as a species we ought to be engaging in is the restoration of relatively degraded soils on degraded farmland to try and bring some of the land that's been taken into marginal productivity back up to at least average productivity by restoring their soils. And I'm fully aware that if you have like really healthy soil, the marginal increase from some of the practices I might advocate might be truly marginal, but on degraded land it can have a huge impact. In other words, no matter how one looks at it, I think, restoring native soil fertility is going to be important for sustaining agriculture in post-oil and therefore post-cheap fertilizer world. We need to start reinvesting in soil fertility as a species to maintain our own productivity in the long run. That's the point I'm trying to make. And I think that alone, the ability to feed the world, would be a reason for restoring the world's soils. It's probably the most important view in my mind. But there's other reasons that I can offer as well. There's a whole connection between soils and climate change. If you can look, you can establish that by the late 20th century, by just a few years ago, fully 1/3 of the carbon that had been added to the atmosphere since the Industrial Revolution came from degraded soil organic matter. It came from plowing up the plains, plowing up Russia, plowing up parts of northern China. And we can actually, if you basically think of the soil as a reservoir for carbon, we've drawn it down historically, well, we can actually start filling it back up. How would we do it? Well, it changes in agricultural practices. By increasing soil organic matter, or by the practice known as biochar, adding charcoal back to soils. What's the potential for actually sequestering carbon at a global scale using these techniques? Well, Rattan Lal, the eminent soil scientist back a decade ago, estimated that if we changed agricultural practices globally to build soil organic matter in soils, we could sequester something like a half a gigaton to a little more than a gigaton of carbon per year. That's enough to offset 10% plus or minus 5% of current global fossil fuel emissions. Now that's obviously not going to fully compensate for global fossil fuel emissions, but a 10% down payment on that in a way that builds soil fertility that helps us feed the world is not necessarily a bad deal. Ron Amundsen, the Berkeley soil scientist, guy who actually taught me soil science, noted that calculated the cultivation and deforestation is still releasing more than 4 gigatons of carbon per year into the atmosphere. That's about half of global fossil fuel emissions. In other words, if we're thinking about how to cut down the amount of carbon in the atmosphere, the whole fossil fuel equation is only part of the issue. Global changes in land use have and continue to be fully 1/3 of the problem. And we're not talking so much about that as a solution, yet we could actually turn that around, and if we could treat soils as sinks of carbon, it could have a huge impact. Biochar is one of the methods that we might be able to use to do that. It's basically charcoal. It's the method that the Amazonian Indians used to build up the terra preta soils. Charcoal is relatively inert. It can last a long time in the soil, and the global soil carbon reservoir is on the order of twice that of the atmospheric reservoir. So if we change global soil carbon contents by one amount, call it 1%, the corresponding change in drawing down atmospheric carbon dioxide is going to be commensurately larger. So if we look at the global biomass decay rate, it's on the order of 60 gigatons per year. It's like 10 times higher than global fossil fuel emissions. In other words, the annual cycling of carbon in and out of the atmosphere from plants and back is 10 times what we're doing with fossil fuels. That suggests that if we could actually capture even just 10%, and I think it's an unrealistically high number, but it's a nice one for comparisons because it sounds small. If we can just capture 10% of the global biomass decay, pyrolyze it, burn it in a low oxygen environment, use the energy that we would get from that burning, and then take that carbon and put it in the ground where it can enhance microbial activity and influence soil fertility, we could completely offset global fossil fuel emissions. Yet nobody's really talking about it at that kind of a scale. I don't think we could ever do it at quite that kind of a scale, but say you did just 10% of that, you're dealing with 10% of global fossil fuel emissions, which if you change practices in terms of other soil organic carbon, the way I was just mentioning, you're already almost at a quarter, dealing with a quarter of the problem right there, without any other lifestyle or impact changes. So the bottom line is I'd like to argue to you that it's time for a new view of the soil. We have to start thinking about soils differently over the next century, however we're going to address them, or we're going to get into the kinds of problems that have faced ancient societies. You simply can't solve problems if you think about them in the ways that got you into the mess in the first place. So let's think very briefly about how humanity has tended to think about soils over the course of our history. For probably most of our existence as a species, we viewed soils as a mystery. Its fertility was something to be personified, deified, and revered. This is Ceres, the Greek goddess of cereals. And for most of our existence, that was probably the way we looked at things. For farmers, since the development of agriculture through till today, soils are a means to a living. Land is there to be worked. That view will always characterize the agricultural sector. But the way that we view soils at a more abstract level has really started to change come the Renaissance. Soil started to be viewed as a decipherable mystery, something we could study and understand. Leonardo da Vinci's famous quote that we know more about the movement of celestial bodies than about the soil underfoot is actually, unfortunately, still as true today as it was 500 years ago. I've been amazed at the revelations in the last 20 years about the role of soil microbiology in influencing soil fertility and nutrient transfers. The basic idea that plants are trading sugars for nutrients that the mycorrhizae and bacteria scavenge out of the geologic materials, and there's an actual underground economy happening where there are symbioses and trading partners. 30 years ago, that was crazy talk. Now it seems to be the way the world really works, and we're just discovering that. Come the 19th century, soil was dominantly came to be viewed as a chemical reservoir, a medium that could be fertilized and topped up with whatever we needed to optimize crop growth. I mean, that's still probably the dominant philosophy in terms of global agriculture. And why has it had such a long run? Well, because it works pretty well. There's no doubt that adding fertilizers has helped increase crop yields globally. In the 20th century, soils became to be increasingly viewed as sort of an industrial input to large-scale industrialized farming as a result of mechanization. I'm not trying to slam mechanization. I mean, it's incredibly helped increase productivity globally, but it has led to, at a global level, the problem that what do you do with the least valuable input to an industrial production process? You don't worry about saving it. And globally, that's what we've been doing with soils for the last century. Now, based on the understanding that we've started to get over the last 20 or 30 years, as the field of soil ecology really came into its own and matured as a discipline, and I like to call it one of the youngest sciences because it really is just starting to blossom. We started to realize that soils are an ecosystem that could be understood and worked with. And therein, I think, lies an opportunity to rethink our basic underlying agricultural philosophy to one where we look at soil ecology. And by that, I don't mean sort of, the Seattle green kind of ecology. I mean the integration of biology, chemistry, physics, hard science into the dynamics of populations in that medium and how it supports life above ground. I mean the real science part of it. How can we, and I think that is where the future of agriculture really lies. And the questions therefore become things like how can we harness the insights of soil ecology to restructure agricultural technology and feed the world based on ecological processes and nutrient cycle. It's a long-term goal that we need to hit that really is not well served by the sort of characterization you see in the media in terms of questions of, well, should we go low-tech organic versus GMO and high-tech agrotech? That's the wrong way to frame things, I think. The real way I think we should frame, even though that's kind of what students in environmental studies classes want to hear. I don't think it's a productive way to think about it. The real question is, how are we going to apply our understanding of soil ecology and the technology that we now have at our disposal to implement that understanding to really solve the problem of not only increasing but actually sustaining crop yields over time frames that a geologist would consider sustainable. We also have a sidelight that I'd like to emphasize before lunch, which will, I promise you, happen in a moment. And that is that I think the call for soil restoration, I'd like to expand to include in urban environments. There have been more than half of humanity now lives in cities. We are officially an urban species from here on out. It's not going to change. That is a sea change globally in terms of just the distribution and nature of human ecology. And there's been enough studies that have come out in the last 20 years that demonstrate the effects of green space in urban environments on social and mental health in people. Everything from if you plant a few trees around an inner city housing project, crime goes down. I mean, there's amazing connections in terms of the way people connect with nature and green space that are hardwired into the human psyche. And that restoring soils, even on small patches in urban environments, could yield major benefits in terms of public health. And I know this because that's the area that my wife works in. And part of it could be from growing fruits and vegetables in cities, but just there's a reason to argue that we should be restoring soils everywhere, not just in our agricultural sector. So key challenges we face, I would argue to you, are adapting farming methods to local soil types and conditions. One of the things I go through in the book is that if you look historically at Western agriculture, we've tried to compel the landscape to adapt to our technology. We need to be much better, I think, at adapting our technology to the variability of the landscape in the future. There's a lot of room for progress there. And we have to learn how to maintain crop yields as the era of cheap oil, and therefore, in all likelihood, cheap fertilizers comes to an end later this century by reinvesting in native soil fertility. How can we do that? Well, we also need to adapt upland farming to reduce soil loss to background levels or soil production levels. That's not such a big problem in floodplain agriculture, of course, and no-till and low-till agriculture provide very effective, proven ways to actually cut erosion down so that we could arguably get close to that background level. Key areas of interdisciplinary research that are emerging, well, how do we actually get organic matter back into the soil? That's not a simple question. We know how we got it out, but how do we put it back in? It's probably going to vary by crop, by environment, by climate, by soil type. It's not going to be a sort of a simple one-size-fits-all kind of an answer, and could involve a lot of research and work this century. How much carbon could we actually reasonably expect to be able to put back into the world's soils? I've seen some rough ballpark estimates, but I consider them very rough. What are the role of ecological and particularly microbial processes in governing native soil fertility? We have the brutal problem that we've actually sort of erased the template that we might have had in terms of restructuring soil microbia historically. And so we're kind of starting in the dark and working. It's going to take us a while, I think, to really figure out the full degree of those kinds of connections. And how can we better address the linkages between soil and public health in both rural and urban environments? And is it even realistic to expect that we could rebuild soil in cities? But the point I want to leave you with is, first and foremost, if we're going to get serious about global soil restoration, we're going to have to stop treating soil like dirt. Therefore, or therein lies, I think, the real message of the title of my book. And I'll just shamelessly plug both the book. I did bring a few copies. If anyone wants to pick one up, I'll sit at the table back there over lunch. And I wrote one on the history of salmon called King of Fish. And also my most recent one, which I ran out of copies yesterday of, is called The Rocks Don't Lie. It's a history of how geologists have thought about Noah's flood. And that one came out last year. But in any case, I'd be glad to engage in questions over lunch. Again, I'll just be in the back of the room. And I apologize that my wife mandated that I get back to Seattle tonight, so I'm going to be heading off to the airport sometime around about 2 o'clock or so. So thank you all very much for your attention, and good luck with the rest of the meeting.